Joining Teledyne Lecroy today for our third webinar in the Essential Principles of Power series. Today's presentation will cover measuring motor performance using power analyzers and oscilloscopes. My name is Hillary Lustig, and I'm the Marketing Communications Manager for Teledyne Lecroy. For some of you, this may be your first event with us, so I'd like to take a minute and introduce our company to you. Founded in 1964 by Walter Lecroy, we are a U.S.-based company headquartered in Chestnut Ridge, New York, where many of our oscilloscopes are designed and manufactured. We were acquired by Teledyne Technologies in August of 2012, and our name changed to Teledyne Lecroy. Our oscilloscopes range from 40 megahertz to 100 gigahertz in real-time bandwidth and include a series of high-definition oscilloscopes that go up to 1 gigahertz in bandwidth, have 12 bits of vertical resolution, and up to 8 channels. We will be exhibiting at the following trade shows in the next 2 months and hope you have an opportunity to speak. Hope we have an opportunity to speak with you if you plan on attending. If you'd like to set up a demonstration time, you can just email me. Today's presenter is Ken Johnson. Ken has over 25 years of experience in the T&M industry. For the past 15 years, he has worked as a product manager for Teledyne Lecroy. His focus is on core application research to obtain a deep understanding of customer applications and needs, and then work collaboratively with customers and R&D here to develop the new products. Currently, he is working on the development of a complete motor drive and three-phase power analysis solutions. He has a BS in electrical engineering from Rensselaer Polytechnic Institute and currently holds the position of Director of Marketing Product Architect. If you have any questions during today's presentation, please submit them at any time via the questions section on your control panel. To keep us running on time, we will hold Q&A at the end of the presentation. Thank you again for joining us. We know how valuable your time is. Ken, I will now turn the presentation over to you.
Okay, thank you, Hillary, and we've got a lot of material to cover, so we'll dive right in. This is part 3. The other 2 parts plus the intro are on the website, and you can download them from there and view them separately. So our agenda for today, we will quickly define power and give a very quick power overview, and we'll talk about solution comparisons, what people use to measure power for single to three-phase systems or for power electronics or for conventional core coil systems as well. And then we'll do some case studies. We've got some great case studies here, a variety of different topics from AC induction motor drives all the way through vehicle propulsion motor and some things in between. And we'll talk about our harmonics calculation option and power semiconductor device analysis as well, and then have some Q&A. So defining the power, this is an intro in every one of our webinar series so far, but power means a lot of things to a lot of different people. So just to be clear on what we mean by that, here are a few of the definitions that you might come across or you might be involved with when people say power. We're only going to focus on a couple of them, though. We're going to focus on, what we call line voltage, current, and power. The AC line input, the sinusoids that feed our commercial buildings and our industrial buildings and our residences. And then we're going to talk about power conversion and the power conversion signals, typically pulse width modulated, and these are parts of bigger systems that require quite a bit of extensive debugging and also power analysis, usually using a power analyzer or a device that performs a similar function. So giving a quick power overview, what I call the 100 years in 7 slides. We'll go quickly through this. Electricity is generated, transmitted, and distributed, and consumed. And historically, the transmission was, and generation and transmission was really done centrally, and then transmission was one way out to the customer, whether it's your house or your business. And the efficiency of that is really very low, 32% overall, really pretty bad. There are a lot of losses in the T&D generation system and the transformers, the power cables, and such whatnot. But what we're seeing is a revolution in that, which we'll talk about in a few minutes. Typically in this system, to measure 50 or 60 hertz systems, there'd be something used to measure the core and the copper losses of that, and that would be a power analyzer, and that device was historically made to measure 50 or 60 hertz power line frequencies and do validation tests and present a certificate to, let's say, a utility or end customer as part of the sale, basically validating that the losses were within acceptable limits. Motors are a big consumer of power. When you look at the size motors that consume the most power, um, it's really follows the 90-10 rule. So 90% of the motors are very small, and they consume only roughly 10% or less of the power. And 10% of the motors are very big, and they consume almost 90% of the power. But overall, half of worldwide delivered electricity is consumed by motors. And really, motors were essentially only line powered prior to the 1990s. Now, drives are really revolutionizing the way that motors are controlled and used, and that's a big part of what we'll talk about today. And there's a lot of government mandates to increase motor efficiency. Motors historically, especially big ones like AC induction motors, are tested on a test stand. The test is usually what I'd call a static load test, so a single load, and there'd be an analog tachometer signal, an analog torque transducer that would feed data to calculate mechanical power. The thing that calculates mechanical power could be this power analyzer, which would also calculate electrical power for the motor and also calculate efficiency. This is what I'd call not an integrated design tool. Limited waveform capture, doesn't really provide dynamic load measurements. It doesn't allow you to look at control signals that are coincident with the power signals. It's not very well suited for small motor test and debug. The power electronics revolution is here, and it's well underway, starting with switch mode power supplies in the 1980s, moving up in complexity and power levels and voltages and number of phases as the decades progressed, and so now we're seeing this everywhere, including the transmission and distribution system. You might hear a lot about distributed generation, and power electronics is one of the key elements that are enabling the change in our transmission and distribution grid to a much more distributed focused instead of centralized generation. All right, so we'll pause really briefly for 1 minute just to ask our first polling question. If you would, just answer this very quickly and tell me what products are you designing and testing. Just pick one or more of these. Okay, we'll provide just another few seconds for the answers to come in and you to complete this question, and then we'll move on to our next slide. Okay, thank you very much. What we're going to do now is we're going to compare solutions. So we talked about power analyzer and oscilloscopes. This is the world most of you know. There's also something called a motor drive analyzer that we'll talk about as well and how that compares. If you look at the solution capability set as a triangle composed of these three things, the first thing being three-phase power analysis. For that, you generally need a fair number of channels and decent resolution, though not necessarily high bandwidth. You need to integrate your motor signals. You get your torque and speed signals. From there, you get mechanical power. And typically any kind of power conversion system includes some sort of control system that makes the power conversion system work. And so there's some oscilloscope capabilities required as well. Typically, the bandwidth's much higher. You need things like mixed signal oscilloscope, digital logic capabilities, serial triggers and decodes. Probably want to look at devices too, the IGBTs and MOSFETs. So scopes are typically used for that. Then for three-phase and mechanical power analysis, the better power analyzers like these here have a motor integration option so they can measure mechanical and electrical power. But these tools, typically, you might have one of these and you might have one of these. They don't communicate well with each other. They're very different instruments. Some of the more fortunate of you may have an 8-channel scope like this one, the HDO 8000, or perhaps some of you own the Teledyne Lecroy motor drive analyzer, which is the 8-channel 12-bit platform, but integrating motor analysis, it's basically three-phase electrical and mechanical motor analysis. So these devices are typically used for static analysis. They give you numbers. The motor drive analyzer is great for static analysis. It can give you a mean value over a short period of time or a long period of time. It can also do dynamic or transient power analysis, let you see the waveforms and the trends. And it can also allow you to debug the things oscilloscopes usually do, meaning the embedded control system. So if we look at this visually, dedicated power analyzer, really it gives you numbers as shown here in this diagram. It's a specialized tool. It looks at your drive as a black box, and it gives you measurements of values of the input and output of the black box. And like I said, some of the better ones integrate simple speed and torque signals as well. There's no controlled debug capability, and typically it has limited waveform capture, typically with the very short records, low sample rate, and low bandwidth. If you look at the comparison of a motor drive analyzer with a power analyzer for static, dynamic power analysis and complete test capability, again, the power analyzer is really only for static power analysis. It cannot handle dynamic power analysis or does not have complete test capability. 4-channel 8-bit mixed signal oscilloscope gets you into the control system here. Everybody knows of this tool to look at your control system. Some may also use it to look at a single device and measure switching and conduction loss. Higher bandwidth, longer records, higher sample rate, but not enough channels. 4-channel scope, if you have a 3-phase bridge, you really can't look at more than one leg at a time and do any kind of significant debugging on your embedded control system at the same time. So a very limited tool, not enough channels. Again, that product does absolutely no power analysis, nothing for static or dynamic, and it's very limited for the complex system that the power electronic system is. Many of you probably use an oscilloscope, a 4-channel scope, plus a power analyzer, and you might wonder, why would I need anything more than this? Well, these tools are separate tools. They operate in different ways, and they're difficult to correlate together to understand control and power interactions. So they operate in two completely different information sets, and so they're not much better than one of these things on their own. Again, they don't do any dynamic power analysis, and they have limited capability for complete test capability. So what we've done, Teledyne Lecroy, we've created something called a motor drive analyzer. At its core, it's an 8-channel 12-bit scope. It goes up to 1 gigahertz. It incorporates power analysis capability in it, both for 3-phase electrical and mechanical. You can see your waveforms. You can get a mean value table like this here, and you can also get a lot of other information as well, which we're going to cover in our case studies. So if we do a quick comparison here, this is all the different instrument types you might be familiar with: the power analyzer, the 4-channel scope, an 8-channel scope, and a motor drive analyzer. And these are the capabilities pictorially represented by this big simplified block diagram. And then these are the different types of areas in that block diagram. And again, a power analyzer, good for numbers, for 3-phase electrical power. The better ones incorporate motor power as well, but nothing else. 4-channel 8-bit scopes, really limited to embedded control system and limited inverter subsection debug. 8-channel scopes are better. At least you can see your power waveforms. And you do a much better job of debugging because you have more channels. But the motor drive analyzer combines the best of all those things. Gives you numbers and waveforms on 8 channels and lets you really dig around in any part of this block diagram and understand what the behavior of your system is. A couple other things that are different about these two products. Basically, both a motor drive analyzer and a power analyzer, they have different ways to select the wiring configuration. You can probe line to line and do a line to neutral conversion. All these tools, both these tools support these things. Basically, they're pretty much the same in that regard. This is a typical power analyzer, of course. That's a Yokogawa, probably the better known one of all the ones that are manufactured. When you look at torque and speed sensing, the motor drive analyzer has a little more capability. It can handle a resolver from the analog speed side for speed and direction, and on the digital speed side, it can also integrate hall sensor information for speed and direction, and a quadrature encoder interface for speed, direction, and absolute position, whereas the typical power analyzers have very rudimentary torque and analog tachometer and perhaps digital pulse tachometer integration. Again, this really stems from the fact that the power analyzer has historically been used as a validation tool on a test bench with a dynamometer, and these are the kinds of signals dynamometers have, whereas designs in the field typically use hall sensors, quadrature encoders, or resolvers. One big difference, the motor drive analyzer is built on an oscilloscope platform. It needs probes. The isolation for voltage is obtained within this probe. That does add cost. It does reduce the accuracy somewhat, although this is a 1% high voltage differential probe. It's the only one like it in the world. So it reduces the accuracy a bit. It does provide more measurement flexibility. I have the ability to utilize this channel any way I want for current or voltage and look anywhere in my circuit here. Plus, I have digital logic inputs too if the product's configured with the MSO. A power analyzer has direct inputs. Looks something like this. These are two different versions here, but the concept is the same. There's banana jack inputs for voltage. There's a BNC and perhaps lugs to feed in your current signal. You can drop the current across a shunt. So you can put a current signal in, drop it across a shunt, turn it into voltage for measurement by the acquisition system. So this is a nice approach. The isolation is built in. The high voltage isolation is built in through the modules. The current shunts are built in. There's options to do some of that in a separate box on our solution. So this is very nice. This is highly desired, but at the same time, there's no flexibility for non-power signals. It's generally pretty difficult on a power analyzer to use any kind of conventional probe like you would use on an oscilloscope. Power analyzers do typically contain other features that are not included in our motor drive analyzer. A lot of times they provide a different calculation basis for power based on voltage and current. Instead of using RMS, they might use RMS mean or rectified mean or something like that. Some of these capabilities are possible using harmonic filter settings in our product. Power analyzers, generally, they're not acquiring data. So since they're not acquiring data and storing it, they can process on the fly. And so they're very optimized for looking at very long durations and measuring energy consumption, which would be great for something like a refrigerator, for Energy Star measurements or something like that. Those are not typical applications for a motor drive analyzer, but is a typical application for a power analyzer. And then they also have some historical features that I'd say are really more dedicated for a 50, 60 hertz core coil world, like corrected power, impedance, or vector graphs, things like that. Typically speaking, that's not what you'd use a nice high bandwidth oscilloscope for. You'd usually use our motor drive analyzer for distorted waveform pulse with modulated waveforms that you obtain from solid state high frequency power conversion devices. All right, so let's pause for a minute for the second polling question. Just choose one of these. Just give me an idea, what equipment do you currently use today for test and validation? Just pick one of these 5 selections for me, please. All right, we'll give just another few seconds for the polling question to be answered, and then we'll continue on. All right, so let's go into our case studies. We have some really good case studies here, people who have used our equipment and in very creative ways. And so let's go through the first one. So the first one is a 480 volt 3-phase 1.5 horsepower AC induction motor drive and motor. And so in this case, the input-output performance and efficiency are measured for very short time periods under no loads and also longer time periods with no load and load conditions. So this is a screen capture from our motor drive analyzer. This is what I call the static or a steady state power analysis. There's no load applied right now. There's 8 channels acquired. We're using a 2 watt meter method for the power calcs. Everything on the left here, you see this tab, it says AC input. These are all the AC acquired waveforms. I have 2 voltage and 2 current. That's how the 2 watt meter method works. And then on the right, we have the drive output, and we're using our Qscape tab display in this case. So these are the drive output signals here. These are my PWM voltage and my current signals right here. There's no load, so there tends to be a lot of noise on the current signal. There's the mean value table right here. This is the numerics table for power. We're just choosing to show the total ABC or input and RST or drive output power values right here. This is the entire 3-phase combination. These things should be very recognizable. This is the efficiency right here. This is the setup summary, so you can see here's a quick summary of what our connection is. We're using 4 channels for voltage and current on the input and 4 channels for voltage and current on the output. The time record here, it's 500 milliseconds total, 2.5 megapoints, and relatively low sample rate, 5 megasamples per second. Very comparable to something that a high-end power analyzer might have. This is that same acquisition, but now without the menu on the bottom open, just in case you wanted a bigger view. And basically here now, what we're doing here is we're still looking at the AC input. I've just chosen a different tab on the right. I've labeled that efficiency. and I've clicked on this right here in this mean power table, if I click on that value, it creates a waveform. And so what we're showing here is this is a waveform of efficiency over time. It's what we call the per cycle waveform. And what it does is it has one value every time there's a cycle. Now what's interesting here is the AC input signal is 60 hertz. The drive output signal in this case is 45 hertz. So they don't match up. They're not coincident. And so basically when you see this signal have quite different periods of time for when the level is at a certain level, it's only because there's a new level calculation for efficiency or a new efficiency calc every time there is a transition in one of these two waveforms. So total there are n different periods here and maybe m different periods here. So you have n plus m different periods here. You can put a cursor on this waveform and measure a value. So you see this cursor is measuring the peak and the min, and you see these values right here. And if I turn the statistics on, you could see that these values all match. So in my value right here, my min and max, those values are represented right here, and the min and max for the efficiency value. And the mean value here in this table matches this value right here. So this really recreates the power analyzer functionality with the addition of the statistical information for all the calculations and the addition of these per cycle waveforms so I can understand behaviors over time. Now behaviors over time aren't very interesting when your drive is in a very steady state condition. So let's take a look at a few more conditions. This is that same setup as before, but under load condition. So it's the same. This is a typo. So this is the same acquired waveform set with my output waveform set here. You can see that the power factor, phase angle, and efficiency improve as would be expected. Under load, we're looking at the same time period as we did before. And now we're plotting these same waveforms. Again, we have the efficiency over time waveform here. This is my efficiency waveform, and I get these values again. It's pretty much the same scenario as before. And here, I counted, there's 28 AC input periods and 22 drive output periods, and therefore there's a total of 50 efficiency calculations. It's one thing to note here is there really is no standard for how do you calculate efficiency on a cycle-by-cycle basis when the input cycle is different than the output cycle. So there's no standard. We're kind of writing a rule book here and being creative. A power analyzer's never had to deal with that because they would just look at the the input power and the output power, and they calculate an efficiency, but you would never know what the per cycle value was. Let's take a look at a dynamic situation where we start the motor at no load, and then we ramp up the load, and we take a very long acquisition. So here is that same drive, and what we've done now is we've captured 10 seconds of data. So it says 1 second per division, but there's 10 divisions in the system. So that means there's 10 seconds total. It's 50 megapoints captured at 5 megasamples per second. What we see here, again, this is our AC input waveforms here on the left and our drive output waveforms here on the right. On the left here, these are the full acquisitions here. You see this highlighted area represents a zoom area, which is shown here on the right. The zooms are represented by waveforms that start with Z, Z1 through Z6 on this side, and they correspond to C1 through C6 here, both in color and number. And then the same is true on the right side for the drive output. I can change the size of the zoom ratio. So here I've made it a lot bigger, so I'm seeing more time in the zoom, and I can see my startup event pretty clearly, very low frequency, ramping up to a very high frequency on the drive for the voltage, and then my current period change as well. Or I can change that zoom ratio to be smaller again and move it somewhere else. And in this case, now I'm seeing some behavior where the drive has essentially reached very close to its steady state condition. You can see here I've clipped a little bit. The product does have the ability to read a little beyond that, but I've decided what I'm going to want to do here is I'm going to want to gate the acquisition. We have a capability called zoom and gate, so we're going to gate the acquisition to the area right up to the point where I've overdriven the amplifier a little bit with this current signal right here. And so we've basically selected a zoom position and ratio. It's variable, so I can make it basically infinitely variable, and I can look at just this particular area right here. And now I'm in a zoom and gate mode, and now the mean value here will be calculated based just on this gated area right here, which is the area shown by the zoom, which is why we call it the zoom and gate mode. And I'm looking again at the 3-phase values for the input and the output and calculating the efficiency. And these are the mean values. And the mean values really, honestly, don't tell you a whole lot. And we're going to show you what that means in a second. So if you take a look at this here, it's the same acquisition, but with the menu, the statistics off. Now we look at some additional information. So here's again our AC input, the same view as before, just arranged a little differently with the DC or the drive output underneath it. We've got our statistics here. We've got the mean value table, and you see now some of these are color-coded with this reddish color. That's because I pressed one of these cells, and when I touch or press that cell, it creates a waveform, and it opens up this table and shows me all the statistics. So I've now got 7 waveforms created, and the waveform is defined by the intersection of the measurement type and the source. So VRMS and sum ABC. If I look over here, I have a waveform that says VRMS sum ABC. It's green. It's this waveform right here. So that's showing me what the voltage value is changing over time. That's pretty constant. It's basically nominally 481 volts, and it's pretty steady. But there are some things that change a lot. So here's the drive output voltage right here, the RMS drive output voltage ramping up, hitting a steady state. And then here is where we put the load on, and you can see the current starts to ramp up. This is the peak current during the startup event right here on the drive output. And what's interesting is the peak current on the drive input happens quite a bit earlier as well, when the drive is first started and you're charging the power electronics section to some extent. And then here's the efficiency waveform here as well. So we can see that the efficiency peaks here, drops off a bit as the motor ramps up the speed, and then the efficiency increases as the load is applied, really as would be expected. But this gives you the ability not just to look at these waveforms or to see a mean value, but to see the trends and how these values change over time, and get some really deep understanding of your circuit. One of the nice things is our Q-scape mode here. I'm operating in this Q-scape dual display mode, so I can look at 2 things side by side. I still have my AC input and drive output waveforms. They're on these tabs. I'm just not showing them. If I wanted to look at all this information at one time, I can connect a big ultra-high def external monitor, and I can just show all that on a big monitor, which is pretty nice. Or I can just use the regular size monitor on my analyzer and look at 4 times the display area deployed, side by side or 1 tab at a time or something like that. Okay, so a quick solution summary here. We showed, both a power analyzer and a motor drive analyzer can do the static power analysis. The dynamic power analysis capability of this product is very rich. There is no corresponding capability here. The input-output efficiency, we do measure that. We measure that with what I call pre-compliance accuracy. If you're really trying to get a certificate for Energy Star or some government cert, this product will be a little more accurate. It's what we would call the gold standard. But a lot of times a design engineer just wants to get a pretty good idea of how things are changing over time. We can do that within about 1.25% for efficiency. So it's still very good, but it's not the gold standard. We did also show something, it's the sync signal and the overlay. That's very nice. It allows us to verify that our setup is correct for period calculation for all the power values. That's very, very important when you have a dynamic event, because there can be a lot of things changing over time. You want to make sure you're determining your periods correctly for all your power calcs. Let's take a look at a brushless DC motor that's battery powered. I just have one simple screen display here. I've shown this a number of times in other webinars. I don't want to beat this one to death. But basically, this is interesting because Hall sensors are used for speed sensing, and we're measuring power at the DC bus, the drive output, and the mechanical shaft output. Here are the Hall sensor signals that we're using for speed, and we've also captured analog torque and speed as well from the dynamometer. This is the drive output. We're doing a zoom in gate. This is the mean value table, and we're plotting 3 things over time: the speed, the torque, and the power. And so you can see how that's changing. And also we have some XY plots here to show torque versus speed characteristics. So this is an interesting example, and primarily what it does is it shows this capability we have in the motor drive analyzer, that we can provide a very comprehensive set of mechanical analysis tools, primarily because we can integrate brushless DC Hall sensors for speed, but also quadrature encoders and resolvers as well. Ability to have. Okay, this is a very interesting example here. This is where we have a very complex drive. It's a small handheld tool. I can't share more information about that um, based on the customer who gave me permission to use this as a example. But what's nice about it is it talks a lot about the control interaction that had to be validated. So the product's a small handheld tool. It operates at pretty high speed. The operation of the tool involves a reversal of motor direction once per second. And they're very interested in understanding what the heat loss is in the motor during operation and reversal. Too high a heat loss is not desired. It can cause user discomfort and reliability issues. And so basically the test and validation challenge here is trying to understand how the control system's interacting with the motor and the drive as it should, and is the output of the drive performing well, and also understanding the power and heat loss during the operation. So what we have here is signals. These on the left here, these 4 signals are the actual full acquisition. We're dealing with 5-second acquisition, or 500 milliseconds per div times 10 divisions. Sample rates reasonably low here. These are control or command signals. High sample rates not critical. This is a control signal to initiate a motor reversal. This is the zoom of that, both in vertical and horizontal. This is a control signal here that indicates expected completion of the reversal, and this is a zoom of that signal over here. You can see the area is highlighted right here. This is an encoder position of the rotor. It's a voltage feedback signal. It's not been scaled into RPM or anything like that, or position or degrees. This basically indicates 0 to 360 travel, and you can see as it's going in one position, it ramps up like this. It reverses right here, and then it starts turning in the opposite direction here. And then these are speed of the motor. That's a voltage feedback signal, and this is the commanded speed. So the engineer was trying to understand if the commanded speed was tracking the actual speed. In this case, both voltage feedback, unscaled, but he was just looking for some rough correlation visually. So the second step was to, and by the way, the first step here was just to verify when this command signal was sent, the motor reversal was initiated, and the motor reversal was completed by the time this command was sent as well. And that can be visually seen right here. Step 2, to verify the drive output behavior. Now we're getting into some power measurements. Again, the customer is using a 2 watt meter method in this case, so he's acquired 2 voltage waveforms shown right here. These are the 2 current waveforms. This is a longer acquisition. It's 5 seconds using 50 megapoints of data at 10 megasamples per second. And what we have right here, this is the motor reversal area. This is the motor operation, and then repeating 5 times throughout this waveform. We're going to show now a zoom of what that looks like. But first, what we're going to do is, for this 5-second acquisition, again, same data set right here. What the customer did was look at the RMS voltage for the drive output, the RMS current for the drive output over time, and the power of the drive output over time. So for instance, in this case, power is the vertical scale, time is the horizontal scale. This waveform here is 5 seconds long. This waveform is 5 seconds long. So this activity is time correlated with these waveforms right here. So you can see what the power draw and consumption is. And if you're astute, you can see in one travel of the motor, one direction, the power is very constant. And in another direction, there's some oscillatory behavior here, which is interesting to know. We're going to look at that a little bit more. Here, the mean value of the table. We can see we're calculating the mean values. Again, the voltage is changing quite a bit. This is the plot of the voltage over time. A mean value doesn't tell me much. Even a statistics set of about 1,000 calculations tells me a range and the mean and the worst case, the standard deviation, but nothing beats being able to just see that value plotted over time. So I've got a lot of data here to look at. If all I had was a mean value in this waveform, I wouldn't have picked up that I might have some problem here with one of the directions of the motor travel. So now if we use our zoom in gate capability, what we can do, again, this is our drive output waveforms. That's the full 5-second acquisition. Then we're going to zoom into one operation of the motor after reversal, operating in one cycle in one direction. And so we're zooming and gating to that right here. We've turned on our drive out sync signal, and you can see these alternate color-coded overlays. From previous webinars, you may remember that represents one of these calculated periods. So we can use that to verify that we're capturing all the periods of this motor operating cycle. Again, this is our RMS voltage, our RMS current, and our power plotted over time. And what we've done by gating, now this numeric table here, it's only showing power values calculated on the zoomed and gated area, which is one operating cycle. And I have time information from my cursor readout right here. So there's one cursor, there's another. The delta between the two of them is this amount of time. So from this power value and this time value, I can calculate the amount of energy, the joules. And this user was very, very clever. He actually set up the drive input, or what we'd call the ABC. He set that up to be the unfiltered, meaning it's looking at the full spectrum of the power. And then the RST, or the drive output setup, is set to look only at the fundamental. So you can see the power level for the fundamental is quite a bit lower by a watt than the power level of the full spectrum. And the difference in that is the heat lost in the winding. So he's able to calculate that as well. So pretty clever application of this tool. Also wanted to measure the power values for a reversal cycle. So now we're looking at this area right here. There's only one reversal cycle. We've picked it up right here through this slight oscillation in the waveform right there. And these are what the waveforms look like during the reversal. That's the power value. And so basically the power during the reversal cycle, or the energy, is just all heat loss. It's all wasted. And so now they know what the power consumption and heat loss is for one operating cycle and one reversal cycle. And that happens once a second essentially, so they could calculate the energy over time. Pretty clever. Now we alluded to earlier, we saw that, again, if this is 2 voltages and currents showing the clockwise rotation, then counterclockwise rotation, clockwise, counterclockwise. This is the power waveforms, both the apparent power and the real power over time. Again, clockwise, counterclockwise, clockwise, counterclockwise, with the reversal shown right here. Now, you noticed earlier, during clockwise rotation, the power value is very constant, but it's very oscillatory during the counterclockwise rotation, which is not necessarily good. The customer was also looking at some of their control signals. Again, this C4 signal right here, that's when the reversal should occur, so he's trying to monitor that. C8 is the speed signal, he's monitoring that. And then these are the encoder position. And here, the C3 and C7 waveforms, basically one is the encoder position, voltage feedback signal, and C7, the other, this blue trace or the red trace, is to censor this calculation. So he was comparing those as well and making sure they tracked. So getting a lot of feedback here. But the primary thing to look at here is, why is this clockwise rotation operating so much better than the counterclockwise rotation? Here's a close-up of that, clockwise versus counterclockwise, a lot of oscillation in the power delivery. You don't see those values here. When you just get a mean power value for this full acquisition, you can't see what's going on. So these per cycle waveforms really give you a lot of information. Based on that information, the customer was able to find the problem in their control scheme, and they modified their control scheme. And once they did that, they took the acquisition again, and the problem is fixed. So now they have much less oscillation than they did before, and the clockwise and counterclockwise rotations match in a much better way. So if we look at the solution summary here for this complex drive and control interaction, the test and validation, again, there's a lot of static power analysis. Both these tools do that same kind of thing. They give you a mean power table value. But for the dynamic power analysis, you can see how helpful it was to have these per cycle waveforms. They have really long continuous captures, statistics, and also be able to use the zoom and gate capability here. Also the control capability. With this product here, you can, especially in 2 wattmeter mode, you got 4 other channels you can use to look at control signals and verify that everything is correlating the way it should. You have no ability to do that on a power analyzer. And with a 4-channel scope, you have limited ability, but then you can't do anything with the power analysis. So this combines everything in one tool, and then it's therefore easy to see the control and power interactions as we described in that example. Okay, we'll take a short break here. I just want to ask you a third polling question. Just choose one of these. I'd really like to know what your principal design and or test role is within your company. Okay, we'll give you a few more seconds just to answer the question, and before we move on to our next case study, we have a couple more to show you. Okay, I think we're just about done here. Waiting just a couple more seconds, and now it looks like we have all of our answers. Thank you very much. Okay, so the next example or case study is a vehicle propulsion motor, and this was something that was measured at a university that's doing what I would call some advanced research and development. It's not a kind of motor you necessarily see in a car today that you'd be buying. So if you see some odd behaviors or things that don't make sense, you just have to kind of put it through that lens. So this is the view right here. I'm looking at the drive output on the left. Again, the customer chose to use the 2-watt meter method here. They're using 2 voltage signals and 2 current signals. If you wonder why one of these current signals looks so much noisier than the other, they were using 2 different types of sensors. So they weren't the exact same kind of sensor. They were just trying to find out if they could do that with our product. So that's why they look so much different. This is our mean power value table right down here. Again, it should look pretty familiar. They're looking at voltage, current, and then the various power values, power factor, phase angle, torque, speed from the motor, and also the efficiency. Now in this case, they have torque signal, which is C5 here. It's this signal up here. That's the torque load cell output. And we've scaled that within our motor drive analyzer signal to get a torque value. This here, that is Z5. This is a vertical zoom of C5. And what's nice about this is not every product, not every oscilloscope can vertically zoom. When you have 12 bits, it's very handy because when I vertical zoom, I can see something very interesting here, which is some sort of periodicity to the signal, and also I can see some ripple. So this was enabled the customer to see some torque ripple in the motor that they hadn't expected to see. This C6 here is an analog tachometer output, and again, that is scaled in our setup program to show values in RPM. And so that's why you get a value here in RPM, and you get a value here in Newton meters. It's coming from the scaled torque and speed signals right here. Now what these signals are here are the per cycle speed and efficiency waveforms. So you can see this is orange, it says speed mechanical, and this is showing the speed. And you can see there's some very regular variation of that speed signal over time. It's varying about plus or minus 1 RPM around this roughly 100 RPM nominal value. And the efficiency plot is showing some variation as well. So what was interesting is here I've indicated this plus or minus 1 RPM peak to peak. If I take that zoom, that vertical zoom of my torque signal, and just slide it down here, I can drag and drop this item right to here, and I lay over on top of that the mechanical plot, the per cycle mechanical plot, I can see there is a very strong correlation of the torque, which is really very interesting. So if you just had a number in this table, you wouldn't see this behavior at all. And so this was very interesting for the customer to see. Now what we're doing is we're using the zoom and gate. Again, these are my original 2 voltage acquisitions here. Again, this is a 5-second acquisition, or 500 milliseconds per div. This customer chose to go with a much higher sample rate, 25 megasamples per second. So they're using a lot more memory. Our product can support up to 250 megapoints. This is using about half that. And the reason they wanted to use so much more sample rate than some of the other examples is because they were also trying to understand the behavior of their pulse width modulated signals. So this is the full 5-second acquisition here. These are the zooms. This highlighted area corresponds to this area right here for the zooms. And notice when I use the zoom and gate this way, then everything's zoomed. So now I've got my speed, my torque signal and my speed signal here are zoomed. This signal here is this signal here, but this also has a vertical zoom on top of it. This is my analog torque signal or tachometer signal for speed. This zoom here is this waveform area right here, but also with the vertical zoom applied to it. So I'm zooming both horizontally by looking at this area right here, and then also vertically by expanding that scale. And you can see that right here. If I looked at Z6, that's 10 millivolts per division, where the original C6 waveform is 50 millivolts per division. Then what I did is I applied a math function. So there's a built-in tool, if you so choose to buy it, where you can put a low-pass filter on. So this F11 trace right here is a low-pass filter of the Z6 signal. and I can filter that. I think it's down at around 10 kilohertz or so. And when I do that, I can see it closely tracks the per cycle speed waveform. So we do have a built-in filter for the speed calculation, and it's using that, and you can see it tracks very, very well. The difference here, this value is displayed in RPM, and this value is displayed in voltage. This is additional capability. Actually, we're just going to be launching this in the next a week or 2 weeks. And this is a harmonic calculation capability, which includes some harmonic filtering on the drive input and drive output. And so, for instance, in this case, selected fundamental plus N. So we're applying a harmonic filter to these calculations, and we're looking at the fundamental through the 10th harmonic. And once we do that, and we know what the fundamental is, then we can establish what the total harmonic distortion is. So we can measure total harmonic distortion as a mean power or a mean value parameter in this table, which are highlighted right here, both for voltage and current. We can also do it for power. And I can get a value for 82 different calculations. And I can take that value, I can click on that table cell, it'll plot that over time. So here we show an orange waveform, that's the current total harmonic distortion for the complete drive output, and the red is the voltage harmonic distortion for the complete drive output three-phase system. And these are plotted over time. Now they are fairly constant, which is reassuring. They're a little bit higher than you'd like, but that's really the design of the motor. As I said, this is a more of a research project, not a fully developed motor that's in a vehicle today. So the harmonic distortion could be one of the trade-offs they're willing to have. In any case, what you can see here is that the THD values are very constant over time. So again, solution summary here for this vehicle propulsion motor. Again, there's a couple instruments that do the static analysis. We showed the dynamic analysis. Again, you saw the zoom-in gauge statistics, the waveforms, and a very long capture time. We have the THD measurements. You do have those here. You just get a value. You don't get the waveform. Here you get values, waveforms, statistics, and so on. And the mechanical analysis here, again, limited capability. It'll give you a value for speed and torque and mechanical power. But here it'll show you the speed and torque. It'll also show you the waveforms and give you a much richer set of information. Okay, two more case studies. One is just to put a little bit of a highlight on the harmonic calculation and analysis option. This is a simple small drive. It's an evaluation board, a small sine modulated drive through vector FOC control. This is the three-phase system here. We've acquired the voltage waveforms, and these are the three acquired current waveforms. You can see it's a very low voltage drive. We are harmonically filtering this to something like the 10th order to calculate the THD. And when we do that, we can calculate a voltage, a current, and a power THD, which are displayed right here. And you can look and say, yeah, this drive looks pretty good. The voltage THD is 3%. The current THD is only 2%. That's not so bad, but when you look at the statistics and you look at the waveforms, you can see there's some big variations, and you can see that the peak voltage THD is almost 7%, just shy of 5% for current. And this might be a little higher. A lot of times there's a 5% limit for a lot of different applications, especially if you're plugging into the line or something like that. So in this case, the zooming gate comes in very handy. We can zoom in to this portion of the waveform. We can see the waveform. We can see there's some distortion activity right there. We can correlate that. So our measurements are only being made on this particular area right here. And then this per cycle waveform will show those three values alone. You can see this is where that high activity is. So I have my peak value is 6.69%. That's represented by this value right here. If I put a cursor on that, it would have indicated 6.7%. So if I had a very long acquisition, the mean table may hide some very significant activities, whereas I could just plot the THD over time and it would jump right out at me and show it to me right away. We also have a ability for you to look at the measurements for the distortion by harmonic order. So this is our harmonic order table. It shows, in this case, 1 through 7, and then there's a slider bar. You can go up to 50 or so, depending on the mode you've chosen, sometimes a little bit more. And then it displays the frequency and the depending on what you've chosen in the table display, you can look at up to 9 of these, but you could look at all 3 voltage, currents, and powers of a 3-phase system on either the AC input or the drive output at one time. Or you could just choose to look at one of them. It's really up to you. And then you can get a spectral display. Like here, you can put a cursor on this, look at a value. You can apply a mask to it if you want. And you can zoom in on them too. So it gives you a lot of capability to analyze the harmonic root cause of high harmonics. So if we look at the solution summary here, again, static and dynamic analysis, that's a recurring theme. Here with the harmonic filtering, the power analyzers do this as well. They're usually hardware PLL based. There's a hardware PLL built into their FPGA, so they pre-process all the data. It does have a very limited operating frequency response rate, so it's really meant only for a static situation where you're in a very steady state situation where the load and the speed and the torque isn't changing very much, because the PLL might not have the ability to capture all the changes in real time for all the harmonics. This is using a software technique. It's a post-process technique, so no matter what the response rate of the system is, we'll be able to capture and measure everything appropriately. There's a THD measurement for us. There is also for most power analyzers. The exception is for us, you can plot the value over time, and that's not true with the power analyzer. Okay, one last case study. Obviously, if you're building inverters and drives and any kind of power conversion system, there's maybe you or there's someone else at your company that's doing some measurements of the semiconductor device, and so that can also be done in our product. Typically, you'll use perhaps a specialized differential amplifier with very good overdrive recovery, very good common mode rejection ratio, some current probes, maybe some of the standard high voltage differential probes to capture the device performance. And then you can measure the switching conduction loss and RDS on safe operating areas, etc. A couple of quick examples of this. This is just showing the acquired drain to source voltage of a MOSFET. This is on a switch mode power supply. So you can see some oscillatory behaviors here that are just the nature of this particular switch mode power supply that the example's drawn from. And this is the drain current measured by a current probe. And this is the conduction state, the off state, conduction state, off state. So you can see it's color coded. And then from that zone identification, it calculates values, and it shows a mean value here. And then it calculates all these different values and shows you what the turn on and conduction loss and turn off loss and the off state. Basically, it gives you a complete set of data for all the switching loss and conduction loss parameters. You can also measure RDS on. So during that conduction cycle, here we only have one cycle just to show what that looks like. Here's the voltage, here's the current. This is where the overdrive recovery of the DA1855A differential amplifier really helps, because I can really overdrive. I'm only looking at the very bottom of that waveform. I'm looking at this portion right here, which means I'm overdriving by maybe a factor of 50x or something in this waveform. So I'm looking at the very bottom, and you can see it's a very well-behaved step. I don't get a lot of oscillation there. Then I measure my current, and I can calculate the RDS on in the zone, and it's going to show me 2.27 ohms. I could also put a cursor on this waveform, and it would indicate that as well. I can do this over very long acquisitions. So now this is showing multiple zones with multiple calculations. This is a mean value here in this table. And there's also a safe operating area plot you can do. You can apply a mask. This is the XY plot of the safe operating area. And here is the failing points where it's just a little bit outside of the safe operating area for the device. All right, so for this solution summary, basically, motor drive analyzer is at its core. It's an 8-channel, 12-bit oscilloscope. It can do all these things. A 4-channel, 8-bit scope with the right tools can do these things as well. You probably have some benefit from having the 12 bits as opposed to the 8 bits, but these oscilloscopes can also perform many of these measurements. They absolutely cannot be done on a power analyzer. So the motor drive analyzer is very complete, and it gives you capability to do just about any testing in your circuit. So if we come back to this and we look at how the capability sets compare, this probably makes a little more sense to you now. You know, you've got 3-phase electrical power analysis and motor power analysis, and power analyzers typically and historically have done those measurements. And then for everything else, whether it's device analysis or embedded control system test, scopes have done that. But the motor drive analyzer kind of sits in the middle. It does all these different things. It has 8 channels, 12 bits. It's a scope that also has power analysis capability. And we've built in, based on the combination of all the inputs and tools, we have the ability to do very unique dynamic or transient power analysis and correlate all those activities back to embedded control system behaviors. So it's more than just one of these and one of these together. It's giving you a lot more capability. Okay, so at this point, we'll pause and we'll answer any questions that anybody has with the remaining 5 minutes or so of our time.
Okay, thanks, Ken. Thanks, everyone. I had a few questions about the recording. So we did record this webinar, and you will receive a URL within a few hours. Also, the slides that Ken presented are available on the right side of your control panel under handouts. And then there's also a flyer for the series, the 3 different webinars that we've done that have a URL for each of them. So the first question is from Alan. I'm looking for capability to measure a motor's power factor, both real and displacement, using only the 3 leads.
Okay, yeah, good question. So I'm going to go back to one of the earlier examples, and we'll look at the AC induction motor. That's a pretty good example. So here you can see, in this case, I have the AC input and the drive output, and I'm calculating power factor right there. So the displacement power factor is typically, when you're referring to that, usually referring to like the distorted waveform of the PWM output, I believe. And so that would be this value right here, and then the real power factor would be the power factor on the AC input. This value represents whatever I've set with the harmonic filter, and so I don't know if I have a picture of the drive output. Let me just, but within the drive output setup tab, there's a place to set the harmonic filter. This is what it looks like within that tab. So I can set that to be on the fundamental only, which will just give me, it'll harmonically and digitally filter and just look at the fundamental waveform for calculation of that power factor. And as you see in this example, this is obviously a different circuit. When you calculate based on the fundamental versus the full spectrum, the power factor will be quite different. It'll be quite a bit higher when you look at just the fundamental. So you have the capability to look at the real sine wave power factor, to look at the displacement power factor, and also to calculate based on the fundamental, the full spectrum, some range or some fundamental plus n. So I believe you can get all the data that you're looking for there. And you can plot it over time. So if I chose to, I could look at this power factor value, I could click on that value in the table, and I could get one of these waveforms that would show power factor over time. Yeah, I thought maybe I had a screen example that showed a power factor over time plot, but I don't. But it can be just like any one of these other waveforms. Okay, thank you. That was a great question. Thank you.
Okay, thanks, Alan. Hopefully that answers your question. I'll reach out to you if not. The next question is it possible to interface LEM current transducer with this product, and is it possible to scale the measurements?
Yeah, that's a good question. So absolutely. There's some literature and information on our website that describe this. I believe there's an app note posted on how to do that. If not, there will be shortly, because I know one was being worked on. But you can interface, customers commonly interface a Pearson CT, Dan Physic, the LEM Dan Physic, the DanaSense CTs. Right within the channel menu, you can directly rescale it. So if you take the BNC output and connect it to the channel input on the motor drive analyzer, which basically is as simple as plugging it into one of these inputs here. Instead of using a probe, you would just plug a BNC in from your CT, from your Dan Physic or your LEM system. The LEMs are voltage output, I believe, and so the scaling is just very simple. If you have a current output from a conventional turns ratio CT, we sell a device called a CA10, which includes which you can build a shunt resistor into, and then you can turn that current output into a shunt resistor voltage output. and then scale that as well. And we have the ability within the channel menu to change the units from volts to amps and to scale it linearly. So yeah, the short answer is yes, you can do all those things. You have complete capability within the instrument, and we're compatible with Rogowski coils, Pearson CTs, DanaSense, DanPhysic, LEM DanPhysic, conventional turns ratio CTs, just about anything. Great question,
Okay.
thanks.
So I also sent you a note, so just let me know. The next question is, I would like to measure current on the DC bus, but the current is carried in traces to the IGBTs. How can I view what is happening on the DC bus with the analyzer?
So I'm not 100% sure the question came through in a way. I'm going to answer it the way you want. So if I don't answer it the way you're looking for, we can have an email exchange. Basically, the analyzer has the ability to let you define a signal, voltage and current signal for the DC bus. So as long as I can pick off a voltage, and as long as I can get a current probe or signal off this DC bus into my motor drive analyzer, then I can get a table of those values as well. So one of the examples, I'm going to jump ahead to that power tool example, which I had the brushless DC motor. Here, what I've got is I used a voltage probe. This was only 18 volt power tool, so I just simply used a passive probe in this case. I got the voltage right here, and then this was a current signal. I just used a conventional current probe that I had, a 30 amp current probe. Again, you could use other things as well. You got to be able to reach down to DC, of course. So our current probe is DC to 50 or 100 megahertz, depending on the rating for 30 amps, and that's all you need. So as long as you can get a signal that represents voltage through a probe and a signal that represents current, either through a BNC cable or a probe into our motor drive analyzer, you can measure all that, and then the DC bus values appear right here in the same table. And of course, then if the drive output follows bus, I can calculate efficiency from the drive output to the bus, and so on and so forth. One interesting thing to note is I was quite surprised when I started getting more involved in this field. There's quite a bit of variation on the DC bus, and here you can see it on the current as the load starts to change. You get quite a bit of variation here, and you actually get some calculated values of very small differences in phase angle on the bus values, and quite a bit of reactive power. So it's quite interesting to be able to look at that as well, provided you can somehow pick off those signals and get them into our instrument. Great question.
Okay, Clay, hopefully that helps. I also sent you an email. Does anybody else have any questions? I think I got them all. Again, thank you for joining us. Again, the slides and the flyer for all three webinars are available to download using the handout section on the right side of your control panel. Ken and our contact information is available in the follow-up email. You can reach out to either one of us, and we'll get back to you if you have any other questions. And thanks for joining us.
Thank you.
Okay, have a great day.
basically validating that the losses were within acceptable limits. Motors are a big consumer of power. When you look at the size motors that consume the most power, it really follows the 90-10 rule. So 90% of the motors are very small, and they consume only roughly 10% or less of the power. And 10% of the motors are very big, and they consume almost 90% of the power. But overall, half of worldwide delivered electricity is consumed by motors. And really, motors were essentially only line-powered prior to the 1990s. Now, drives are really revolutionizing the way that motors are controlled and used, and that's a big part of what we'll talk about today. And there's a lot of government mandates to increase motor efficiency. Motors historically, especially big ones like AC induction motors, are tested on a test stand. The test is usually what I'd call a static load test, so a single load, and there'd be an analog tachometer signal, an analog torque transducer that would feed data to calculate mechanical power. The thing that calculates mechanical power could be this power analyzer, which would also calculate electrical power for the motor and also calculate efficiency. This is what I'd call not an integrated design tool. Limited waveform capture, doesn't really provide dynamic load measurements. It doesn't allow you to look at control signals that are coincident with the power signals. It's not very well suited for small motor test and debug. The power electronics revolution is here, and it's well underway, starting with switch mode power supplies and the width when people say power. We're only going to focus on a couple of them, though. We're going to focus on what we call line voltage, current, and power, the AC line input, the sinusoids that feed our commercial buildings and our industrial buildings and our residences. And then we're going to talk about power conversion and the power conversion signals, typically pulse width modulated, and these are parts of bigger systems that require quite a bit of extensive debugging and also power analysis, usually using a power analyzer or a device that performs a similar function. So giving a quick power overview, what I call the 100 years in 7 slides. We'll go quickly through this. Electricity is generated, transmitted, and distributed, and consumed. And historically, the transmission was, and generation and transmission was really done centrally, and then transmission was one way out to the customer, whether it's your house or your business. And the efficiency of that is really very low, 32% overall, really pretty bad. There are a lot of losses in the T&D generation system, and the transformers, the power cables, and such whatnot. But what we're seeing is a revolution in that, which we'll talk about in a few minutes. Typically in this system, to measure 50 or 60 hertz systems, there'd be something used to measure the core and the copper losses of that, and that would be a power analyzer, and that device was historically made to measure 50 or 60 hertz power line frequencies and do validation tests and present a certificate to, let's say, a utility or end customer as part of the, say, 1980s, moving up in complexity and power levels and voltages and number of phases as the decades progressed. And so now we're seeing this everywhere, including the transmission and distribution system. You might hear a lot about distributed generation, and power electronics is one of the key elements that are enabling the change in our transmission and distribution grid to a much more distributed, focused, instead of centralized generation. All right, so we'll pause really briefly for 1 minute just to ask our first polling question. If you would, just answer this very quickly and tell me what products are you designing and testing. Just pick one or more of these. Okay, we'll provide just another few seconds for the answers to come in and you to complete this question, and then we'll move on to our next slide. Okay, thank you very much. What we're going to do now is we're going to compare solutions. So we talked about power analyzer and oscilloscopes. This is the world most of you know. There's also something called a motor drive analyzer that we'll talk about as well, and how that compares. If you look at the solution capability set as a triangle composed of these three things, the first thing being three-phase power analysis. For that, you generally need a fair number of channels and decent resolution, though not necessarily high bandwidth. You need to integrate your motor signals. You get your torque and speed signals. From there, you get mechanical power. And
Joining Teledyne Lecroy today for our third webinar in the Essential Principles of Power series. Today's presentation will cover measuring motor performance using power analyzers and oscilloscopes. My name is Hillary Lustig, and I'm the Marketing Communications Manager for Teledyne Lecroy. For some of you, this may be your first event with us, so I'd like to take a minute and introduce our company to you. Founded in 1964 by Walter Lecroy, we are a U.S.-based company headquartered in Chestnut Ridge, New York, where many of our oscilloscopes are designed and manufactured. We were acquired by Teledyne Technologies in August of 2012, and our name changed to Teledyne Lecroy. Our oscilloscopes range from 40 megahertz to 100 gigahertz in real-time bandwidth and include a series of high-definition oscilloscopes that go up to 1 gigahertz in bandwidth, have 12 bits of vertical resolution, and up to 8 channels. We will be exhibiting at the following trade shows in the next 2 months and hope you have an opportunity to speak. Hope we have an opportunity to speak with you if you plan on attending. If you'd like to set up a demonstration time, you can just email me. Today's presenter is Ken Johnson. Ken has over 25 years of experience in the T&M industry. For the past 15 years, he has worked as a product manager for Teledyne Lecroy. His focus is on core application research to obtain a deep understanding of customer applications and needs, and then work collaboratively with customers and R&D here to develop the new products. Currently, he is working on the development of a complete motor drive and three-phase power analysis solutions. He has a BS in electrical engineering from Rensselaer Polytechnic Institute and currently holds the position of Director of Marketing, Product Architect. If you have any questions during today's presentation, please submit them at any time via the questions section on your control panel. To keep us running on time, we will hold Q&A at the end of the presentation. Thank you again for joining us. We know how valuable your time is. Ken, I will now turn the presentation over to you.
Okay, thank you, Hillary, and we've got a lot of material to cover, so we'll dive right in. This is part 3. The other 2 parts plus the intro are on the website, and you can download them from there and view them separately. So our agenda for today, we will quickly define power and give a very quick power overview, and we'll talk about solution comparisons, what people use to measure power for single to three-phase systems or for power electronics or for conventional core coil systems as well. And then we'll do some case studies. We've got some great case studies here, a variety of different topics from AC induction motor drives all the way through vehicle propulsion motor and some things in between. And we'll talk about our harmonics calculation option and power semiconductor device analysis as well, and then have some Q&A. So defining the power, this is an intro in every one of our webinar series so far, but power means a lot of things to a lot of different people. So just to be clear on what we mean by that, here are a few of the definitions that you might come across or you might be involved